you guys got the right answer if you took a shot at guessing or deriving the correct answer. So to do this, one thing to notice is with cosine, what the Laplace transform looks like. We have s divided by s squared plus a squared, right? So number s is the item that doesn't change in a Laplace transformation. Everything that is an s likely has a variable that's changing and fluctuating. So it's cosine of a times t, right? So if we do this correctly and we look at the Laplace transformation piece by piece of cosine of 4 times t, for example, the first thing you should have done is probably pull out the 4, okay? So then you end up with a Laplace transformation of cosine of 4t. Okay, that should be the first step you did in your head or on paper. And then the next step is to identify what that a term was. So here, a is equal to 4, right? A is equal to 4, so the Laplace transform should be the following. It should be s divided by s squared, okay, plus a squared. Well, a is 4, so that's 16, right? And so if you were to simplify this, the Laplace transformation then becomes 4s all divided by s squared plus 16. Not too bad, right? It's pretty simple. So if you got that one right, you probably got the rest right as well. So if we do Laplace transformation for completeness of -9 sine of 4t, okay, you should have gotten the following. Again, you should have pulled out the constant first, then done a Laplace transformation of sine of 4t, okay, like this. And again, this would give you -9, but now we're going to be able to use what we derived before previously in this series of lectures. And note once again that a is equal to 4, correct? So since a is 4, then what we have is the following. We'll have a on top instead of s. So again, just make sure I write this down. A is equal to 4, so we have 4 divided by s squared plus a squared, which is 4 squared, so that's 16. Okay? And just so you guys know, it's coming from this term up here. That's where all of this is coming from. So simplifying that would give us very clearly -36 all divided by s squared plus 16. Okay? Not too bad at all. And then the last one, I'll leave to you guys to solve. But I'll just write down what the answer will be. If you do the Laplace transformation of 2 times the cosine of 10t, okay, you should get 2s, okay, 2s divided by s squared, okay, plus 100. That's what you should get. So altogether, you should have this solution, this one down below, though these two are the same. You want this one, and this one, okay? And you just add those three together, and that would be the Laplace transformation for g of t up here, okay? All right, so now let's go ahead and talk about how we can solve an initial value problem with this equipped in our arsenal. So the first thing we got to do is write down a few additional facts that go with differential equations and that are commonly used with Laplace transformations. So we go ahead and write down a little fact that's going to prove to be extremely helpful for us in these next two videos that we do. Let me just check. Yes, next two videos that we do. So, so the fact is this. Suppose Suppose that f, okay, f prime, which is the first derivative, f double prime, second derivative, and so on. And this would be f of whatever order of derivative we're taking, minus 1. Assume these are all continuous functions. Okay. Assume they are all continuous functions. Okay. And f to the nth order, and this is the key thing right from the beginning, is a piecewise continuous function. Okay. Then we have the following. Okay. The Laplace transformation of f to that order, okay, is going to equal s to the n times the transformation f of s minus s to the n minus 1, so 1 power down, times f of 0, okay? And we're still talking about Laplace transformations, by the way. Minus s n minus 2 f prime of 0, okay? Minus, notice all the minuses here, minus s times f n minus 2, 0, okay, of 0. So notice these are relating to the functions, okay? Lowercase f refers to the original function and the particular order of the derivative that it's referring to. Capital F refers to the Laplace transform, okay? And of course, these zeros here with the function referring to the initial values that we're using, all right? So to conclude this, then it's subtracted from f n minus 1, 0, okay? So the idea is it looks through every single possible derivative and its Laplace transformation. All right. And there are two special cases that will be very useful for us. So let me go ahead and describe that. Since we're going to be dealing with second order differential equations in this class, more often than others, it will be convenient to have the Laplace transform of the first two derivatives. Okay, but you can easily apply this formula that I've shown you to any order of derivatives. All right, so let's do a Laplace transformation of the first derivative using this fact that we just derived. Okay, so this is going to be equal to s, all right, times capital Y of s, all right. So this refers to f of s, as you can see. I'm just using y instead of f here, as you can see. So if this was f prime, like it says up here, this would be capital F of s. Okay, I want to make sure you guys don't get confused by notation. That was just changing nomenclature. Okay, so that's this. And since if you take the power here, or the order, which is one derivative, well, that's what n is. So the power or the order is 1, first derivative. Okay, that's what informs you what n is. And it reaches 0 right away. There's no, fourth order, third order, second order, then first order. It immediately gets to the 0th order pretty quickly, okay? And so f to the 1 minus 1 is 0, so that's, 1. So that's essentially referring to the initial condition, which is this last term that you see over here on the very, very end, okay? So you only have two terms you're playing with here, the first term here and the last term here. And that's how you compute the Laplace transformation of the first order, okay? So now we can do the Laplace transformation of the second order. y double prime. So here the order is equal to 2, just so you guys can see that. And so what this is going to equal is s. Notice that n is no longer 1, now it's 2, so it's s squared, okay? And it's capital Y of s, which refers to the Laplace transformation. And this is being subtracted from s. You go down 1, right? And minus 1, which is what this is referring to, the second term. So it's s to the first power times y of 0, not f of 0, okay? And again, after 1, now we're back down to the 0th power again, so you could probably guess what this next term is going to be. But you might be a little confused by what you see, because what will end up happening is you get y prime of 0. Take a moment and look at that. Why do you think we get y prime of 0? So first of all, notice that the two function evaluations that appear in these formulas, y of 0 and y prime of 0, are often what we've been using for initial conditions in our initial value problems. So this means that we are to use these formulas to solve an initial value problem, and we will require initial conditions at t be equal to 0. So take a moment to look at this, but do you see where this comes from? It comes from the fact that order is 2. Okay, so this last term is 2 minus 1, right? So the last term is still 2 minus 1, so that's f prime or y prime of 0. So I want to make sure you guys can see that. So that's where some of the confusion comes from. It's still the last term, but it's referring to the derivative of the last term, okay? Notice that it's increasing the order depending on the size, and then it's the last derivative that gets subtracted here, 1 minus the order of the last derivative, okay? So that's a good one to practice to make sure you guys cope and understand that, because this is the Laplace transformation of the second order, and we will see that again and again. All right, so armed with these two pieces of information, we will then go ahead and solve an initial value problem. And then once that problem is solved, that will complete our lecture today. And then immediately on Thursday, I'll show you guys how to solve systems of linear equations with differential equations and use Laplace transforms to solve those complicated situations. See you soon.